session from Green RWA about energy and the way technology and energy innovation will be able to get through net zero transformation. I'm Olivier Vinciguera, and this is the agenda. I'll be talking 5 minutes about Green RWA as usual for the most active participants of the association, or even people outside the network, because this meeting is public and is recorded, by the way, so you will be able to hear about it again. And then we'll go straight to Karim for his presentation, long duration energy storage, and usual Q&As at the end, so don't be shy. You can ask questions as much as you want, and we stay online until we're through. So a few words as usual on the network for external joiners. I'm the chair of the association Green RWA, which aims at accelerating the green transition by aiding banks to analyze, optimize their climate risk capital budget through open collaboration. So basically, the idea is to say that banks need to finance the transition, that the transition is possible specifically through innovation, and that's why we like to talk a lot about energy and connect, in a way, the industry, the real economy to the finance world. I think it's very important to connect both and also to educate people from our financial community to all these new transformative technologies in a way. We have now 85 individual members, still 9 corporate members. We have, we have 18 new members in the beginning of the year, and the goal will be to be 100 this year. We want to be we have a very focused network of participants and supporters of our cause, and we think it's a good place to be. We are counting, of course, now this is the 17th event, but as I said at the beginning, the 4th on energy specifically. So a couple of news about Green RWA. One thing which is very critical to our work is that the Bank of England and the PRA, the Prudential Regulation Authority, are organizing a conference in Q4 of this year on climate change and capital. The goal is to adjust the capital framework to take into account climate-related financial risks, very much our core cause, I should say, and also use that. This is really quoting the Bank of England, used to inform life policy development at the bank and the PRA. So we are submitting today the white paper on the climate extended risk model, the latest version as published by Jocelyn, Jean-Baptiste, and Anne. And we gathered the signatures of all the board members of the association today. Thank you, Adrienne, Loïc, and Jean-Baptiste for that, to support this paper. The goal is that this paper is selected by Bank of England to be presented at the conference in October, and hence being a speaker and give a full visibility on our work in UK, where I think it's a place where we still need to make progress, and not only because there is room for space, but because Bank of England is very, very strong and has embraced the climate change clause a while ago, so we want to be part of their framework. So please support us. When you will see LinkedIn post about that, if it's not today, it will be tomorrow. Please support us to push as much as we can online in the different media our work and our goal here to be part of Bank of England conference. We're also actively engaging with the World Bank and with the IFS, with meetings coming up in July to present our climate risk approach. As you know, this is very much in line with our engaged policy to try and meet central banks as well as international or supranational institutions. So we've already met BEC, Fed, IMF, and we've got a great supporter from that point of view with Charlotte Gall, who will be, by the way, hopefully be able to participate to this meeting with World Bank. So we're very keen, and very happy with this movement on green RWA and our work with the different international institutions. One thing Walid, our marketing manager, proposed is to open our documentation center, on which there is a continuous work from Walid and also from Nicolo from US on the day-to-day, is to feed this documentation center. So we're going to open it for a week so that anybody can access it and see the wealth of information that we're trying to get access to. Of course, very focused on climate-related financial risk. I believe Walid is going to share this link as we talk, that you can directly see from it the directly access documentation during that call, or to keep the link for later consultation. These are the menus. So this will be open for 1 week, to be clear. So let's move now to the main topic of the day, and the main guy of the day, if you allow me to say that, Karim. We're welcoming Karim Wazni. He's an expert in the renewable power sector. I will let you, Karim, introduce yourself in more details and explain where you come from and assess your position into this sector. But I have to say, I'm very excited about this session, because I think it will give a great view on the fundamentals and the necessity to deploy LDES in a world where renewable energy is developing very quickly, but where sometimes the intermittency inherent to solar and wind capacity is challenged by a number of people. So I think it's very important to give a full view, including economically, about LDES. Having said that, Karim, the floor is yours, and I'll let you take over the presentation.
Thank you very much, Olivier, for the introduction. Okay, can you hear me okay?
Perfect.
Great, and thanks for having me on your session. Yeah, very excited to share a sort of landscape on long duration energy storage. I've looked at the attendees list. It's quite broad, from a number of countries and quite a lot of people actually who have energy storage as a title or background, or who are involved in consulting in that space. So I hope the questions will not be too difficult to answer. So before, let me just share my screen now. Let me know, Olivier, if that comes up okay.
Yeah, I can see it there, Karim. Yeah, I can see that.
Great.
Thank you.
Thanks. So let's move on. So today we'll talk about the agenda is around 3 topics. First of all, is what is long duration energy storage and how is it defined? Second, what kind of technologies are out there that are focused on long duration storage, and what are the characteristics? And third, what does the market look like for this technology? So without any further ado, let's jump in. So I think a number of you are familiar with the ambition that the world has to move to net zero by 2050. And the IEA has published a few months ago a scenario that essentially charts the way to a net zero world in 2050. Now, whether we reach that in time or not, that's a different question. But what's interesting about it is, what are the implications that this scenario puts, or what are the sort of ambitions that it puts on all of us? And the first implication is quite obvious, right? It's that we're going to have to grow the installed solar and wind capacity by quite a lot. And as you can see from the upper part here, where we are in 2020, we were on a rhythm of about 350 gigawatts of wind and solar per year installed, of new capacity installed. This pace will have to be tripled to about 1,000 gigawatts a year starting from 2030. So we have a ramp-up phase which is going to be pretty steep between 2020 and 2030, and then we'll have to sustain that. Now, that's great, and if we can achieve that, we'll have a lot more zero carbon renewable generation. The only issue being that the type of generation we'll have, which is solar and wind, is highly intermittent, and it's difficult to predict. So it is actually a big challenge for the grids as they are designed today, because first of all, because of the intermittency, we might see, and we're already starting to see in some areas, imbalances between power supply and demand. And it's becoming more and more difficult for grid operators to keep the grid in balance at all times, and make sure that the power production equates to the load, to the consumption. Now, the other challenge is that we designed our whole grid over the past 100 years from a very centralized standpoint, with very large power plants and feeding into regional hubs and then into distribution to the end consumer. But we did it in a sort of static way. So we didn't expect that actually those large power plants would one day have to be supplemented or replaced by large amount of distributed generation that could be in a completely different geography from where the large plants were set up. So that poses a big challenge in terms of the flows of energy that are going through the transmission system. The third aspect is a bit more technical, but it's around system inertia, meaning the ability of the grid to maintain its operating condition, whether in voltage or frequency, when an event happens. For instance, the loss of power or the failure of a generator, or a big swing in renewable generation. So those are the three big challenges that those intermittent renewables are posing, and the fact that they are not rotating machines, but they are inverter-based technologies. So the consequence of that is that it is expected that battery storage will be absolutely essential to manage those grid challenges and to balance the load and the generation. And that grid will be also needed to be reinforced in order to accommodate those transmission flows. So battery storage is expected to grow from about 18 gigawatts of battery capacity installed in 2020 to about 3,000 gigawatts in 2050, which is also a tremendous acceleration compared to the current rhythm. So this is why energy storage is really, at the top of the agenda in terms of achieving the 2050 targets. Now, going back to basics, what is energy storage, and what is the most common way to store electricity these days? So you'll all be familiar with hydro power and with dams, and the fact that when water flows from an upper reservoir into a lower reservoir, you can convert that gravity potential energy into kinetic energy, and then from that kinetic energy run essentially generation. So pump storage power plants converts that kinetic energy from the water coming down the hill into electrical energy, and it keeps it in the lower reservoir. Now, this is about generating power. Now, when you want to recover that power, you essentially reverse the process. So you pump up the hill the water that was in the lower reservoir, and pumping up the hill essentially requires electricity. So it's going to store electricity in the form of gravity power or gravity potential energy in the upper reservoir. Now, why do I go back on that? First of all, because this is the most common way to store electricity, because there is about 9,000 gigawatt hours of capacity worldwide estimated with this technology, or 160 gigawatts of power that can be delivered through those pump hydro storage plants. Now, a few definitions here. So energy capacity, that's going to be the gigawatt hours, the megawatt hours of electricity that can be stored by a an energy storage system. Power rating, this will be the amount of power that storage system can either generate or absorb from the grid. For hydro, it's typically in the hundreds of megawatts. Round-trip efficiency, that's the efficiency of the whole system from the energy delivered to the grid, ultimately, to the energy that was originally absorbed from the grid. So we have losses occurring in any energy storage systems, but typically they're quite reasonable for pumped hydro in the range of 80%, in the range of 20% losses and 80% round-trip efficiency. Now, the discharge duration is the time during which that storage system can deliver the electricity to the grid at its power rating. Okay, so moving on. So storage applications can be segmented by different types of power class and discharge duration. And you can see the application on the left side there, ranging from short-term power stabilization. So 3 categories: very short duration, and long duration. And the top category is really around power quality and grid stability in the short term. The second category, short duration, that will be around peak shaving, for instance. So a consumer that has a load that peaks during the day may see their electricity bill quite high go up because their demand is high, and they may have to pay a lot of money just because at some point during the day they ask for the grid for a lot of power. With energy storage, you can actually shave that peak and discharge an energy storage system, so you lower that peak consumption, and then your electrical bill will come down. Spinning reserve is another example of short duration, where you have a generator that's standing by, and it's standing by ready to pick up in case of a failure, an unexpected event that happens on the grid. So another generator tripping, for instance, that could be one such event, or a surge in the power demand from turning on a motor. So there's a number of events that require essentially robustness, resilience from the grid, and that's one of the applications of energy storage. And the last one, but not least, is what we're concerned about today, which is long duration energy storage, and what are the applications of that. So we'll come back to that in a later slide, but essentially it's around matching generation and load. It's around firming renewables, and it's also around long-term and seasonal storage, which is measured in sort of the ability to deliver power during weeks. So you can see the sort of scale in terms of discharge duration that goes from a few seconds at the top to several hours as you go down that table to weeks, which is what we would define as seasonal storage. Now, how it is defined is, there is no clear definition, but essentially people generally accept that a storage system that can discharge for 10 hours or more of rated power will be a long duration energy storage system. And the other characteristic that people will look at is what is the cost of storing the electricity in that system, and is that cost sufficiently low on a per kilowatt hour basis, essentially in terms of energy capacity. All right, so I'll go on to the next slide just to illustrate that point. So this is an expected trajectory, cost trajectory for long duration energy storage, broken down into its power component and its energy component. So essentially, if you refer to the analogy with pumped hydro, the power component would be essentially how much does the pump or the generator cost per kilowatt of capacity that it has, and the energy component would be how much is the cost of digging that upper reservoir and that lower reservoir so they can contain a high volume of water, and what is the marginal cost of digging an extra amount of soil to put more water that will deliver an extra kilowatt hour of electricity. So that's how you should think about those two components. And typically in long duration energy storage, they are decoupled. So you can choose the size of the pump independently of the size of the reservoir. This is not quite the case for batteries, that often come with a fixed combination of power and energy. Now, what you can see from this table is that actually there are two types of energy storage, long-duration energy storage archetypes that are defined by the council, the LDES council. One is very long duration, and the other one is very low, is sort of 8 to 24 hours. And they have different cost profiles. So we'll come back to that later. Now, let's go into use case. So why do we need long duration energy storage? And I'll stop on this one for a second. So imagine that you are a remote microgrid, and you have to deliver your own power with a combination of diesel, solar power, and battery storage. And you can see in the table below the characteristics of lithium-ion costs and capex and long-duration energy storage. But essentially what happens is you will want to run as little diesel as possible, because the cost of running on diesel, it will be very high. It's around 30 cents per kilowatt hour or $300 per megawatt hour in this particular instance. Whereas the cost of solar energy on the long-term basis is these days almost unbeatable. It will be in the range of $60 per megawatt hour. So you want to maximize the amount of solar energy you're using, minimize the diesel fuel you're using. So what do you need to do then? You need to oversize the solar power, which you can see on that middle graph here, and produce that solar power will produce at its peak at noon, but you're going to store that excess power into the battery, and then you're going to discharge it when the sun comes down. Now, when you do that, and you start to increase the fraction of renewable electricity that you have in your mix, then your mixed cost of electricity is going to go from almost the cost of diesel at 0% fraction of renewable, all the way down to almost the cost of solar by itself, except that it's solar by itself plus storage, because you need to add energy storage to be able to increase your penetration of solar power. So you get this blue line, which is essentially your blended cost of electricity, which is a sort of weighted average between the diesel and the cost of solar and storage together. And what that means is, in order to achieve those high levels of penetration, looking at the graph at the bottom here, that means you're going to have to deliver, or you're going to have to have a storage duration or storage capacity that will go into the 10 to 12 hours of energy storage in order to reach that level of penetration and lower your cost of electricity by taking advantage of solar. All right, so I'll go quickly on the second use case. So the second use case is a study done by the French Agency for Energy Efficiency and Environment in 2015. And they were looking at what would be the optimal mix of renewables and energy storage to reach the lowest possible cost of electricity in the event that France wanted to run without nuclear power. Now, what's interesting about this is, first of all, the estimated cost of electricity was actually quite reasonable, in the range of 120 euros per megawatt hour, which is very close to actually what nuclear can do today, which can actually be more expensive than 120 euros per megawatt hour. Now, the other insight that we can derive from this study is that you can see from the bar charts that increasing the renewables penetration up to 80% does not require seasonal storage. You can essentially do that with a combination of renewables, short-term and long-term storage, short-term being defined as 6 hours of storage, and long-term being defined as 32 hours, up to 32 hours of storage. So seasonal storage is really required when you're pushing beyond 80% renewable penetration and trying to get to 100%. So that was an interesting finding. The second finding, or the second use case that's interesting, is a recent study by Timera Energy, which is a consultancy based in the UK, that sort of describes why the UK is going to need more flexibility. And that's looking at the top chart left here, we are looking at very big swings of renewable power coming from wind and solar. So in 2021, the variation in wind can create, on average, a 5 gigawatt swing in the power generation. But the maximum range is between 10 and sort of 2 gigawatts. However, in 2030, with the increase in wind power deployed, the swings will be up to 16 gigawatts on average. That means you need a huge amount of flexibility and other generation or storage that can pick up the slack when either the wind increases or it decreases. Yeah, I mean, the other part of the chart on the right side looks at periods where, on average, you have very low wind loads beyond the average capacity factor, which can, last for 3-4 weeks, and whether it's in the summer or in the winter. And during those periods, then you do need another source of generation, whether it's having stored excess wind that happened in the weeks prior to those events, or whether it's clean, flexible generation, such as H2 hydrogen peakers. You will need something else than just short duration storage and renewable generation. Now, what about hydrogen? How does that compare with long duration energy storage? And one way to compare the two is to do it on an economic basis, looking at what is the levelized cost of storage. There is a formula I've sort of picked from one of the typical ways that levelized cost of storage is calculated, and it's very similar to levelized cost of electricity in the sense that it's a discounted present value of a capital cost divided by the amount of energy and the throughput through the energy storage system. Now, without going into details, looking at the chart below, you have a range of levelized cost of storage comparing hydrogen and long duration energy storage. And this range essentially indicates that for durations that will be beyond 100 to 200 hours, hydrogen is going to be more competitive in terms of cycling electricity through that. However, long duration storage will be a more effective way to do that in below, let's say, 50 hours or so. Now, in order to do that, you do need to be able to charge the systems with very cheap power. So the assumptions in the chart are around a $30 per megawatt hour cost of electricity that you're using to charge either the storage or produce hydrogen with your electrolyzer. Now, I just wanted to put that in perspective with what's the reality today on energy markets. And today, you can see the chart on the right there, which is the Germany wholesale prices from last week. The average, I don't know if people can read, but the average is around $250 per megawatt hours, which is about 7 to 8 times the assumption on the left there. So from this, it is quite obvious that you cannot really deliver a very effective cost of electricity if you charge at $250 per or euros per megawatt hour with a 33% round trip efficiency, because that would lead you to delivering electricity at 3 times that, which is around 750 euros per megawatt hour. So that doesn't make any sense. Now, so what's the alternative? How do you do this with hydrogen? Well, a lot of people are thinking actually hydrogen will be manufactured at huge scale in countries such as Australia or in Africa, and will be shipped and delivered at the cost indicated on the left chart, so that it can be used to provide the peaking power that some of those European countries will need when wholesale prices are high and renewables are low. Now, I'm going to speed up a bit because I realize time is going by quickly. So in terms of technology, there's really 4 types of long duration energy storage technologies, which are thermal, so heat storage, mechanical, chemical, or electrochemical. Now, maybe a focus on three technologies that I think are interesting, and some of you may not be familiar with. So the one on the left is from a company called Stolect, and the concept is called pumped heat energy storage. So this is the same concept as essentially a heat pump, for those of you who are familiar with that concept, where you take electricity in and you create two reservoirs of temperature, one high and one low temperature. Normally, this would be used for heating, for instance, or cooling. But in this case, you just store the heat at high temperature or low temperature, and then you reverse the cycle. So you turn that temperature difference into electricity, back into electricity. That's one example. Energy Dome is also a startup that's developing an interesting technology, which is similar to a refrigeration cycle, where they are storing electricity in the form of liquid CO2. So they are liquefying CO2 using electricity, and then essentially vaporizing CO2 to produce power. And the last one is HydroStore, which is an adiabatic compressed air system. The principle being that using electricity, you compress air, you generate compressed air and heat, you store both of those, and then you reverse the cycle again, you mix the air with the heat, and you regenerate electricity. Now, I'll skip this slide, which you can consult at a later time, but this is essentially an overview of the types of companies that are operating in the long-duration energy storage space, belonging to the four categories that we've seen before, but also segmented by the maturity of their technology and the scale of their technology. So most of the sort of mechanical technologies using adiabatic compressed air or liquefied air or gravity-based systems will be sort of targeting very large systems compared to, very comparable to pumped hydro. Most of the electrochemical forms of energy, so batteries, long-duration batteries, would be sort of smaller scale with the ability to scale up, but not necessarily have large economies of scale. I would say that it is extremely challenging to bring to market new storage technologies. And I can talk with experience, having been in startups that were working on those, introducing those technologies. And really the challenges are sort of, you can break them down in two categories. Electrochemical batteries, the challenge there is not so much proving the technology at small scale, because you can do that with a reasonable amount of funding, but it will be around scaling up and proving that you can improve your cost and improve the performance when you start manufacturing at scale. And it's also around the funding of that large-scale manufacturing. Whereas the other technologies, which are very large scale, such as compressed air or liquid air, the challenge there is actually the opposite. It's about doing your first prototype at a small scale. And usually that's very difficult because those technologies are best suited to, for instance, large turbines. And you can't really take a large turbine and do a small prototype with a large turbine. So the challenge for those technologies is to actually do a first prototype at scale that proves that it's going to work before actually being able to repeat that in a series production. All right, so what does the market look like? And this is very much borrowed from a study by McKinsey. Now, this is just to give a sense, but people are expecting that long-duration energy storage will be needed and will develop in the range of terawatt-hours of capacity. And the biggest, across various segments and applications, really the dominating segment is large grids, where long-duration energy storage is connected into the grid, a bit like a large pumped hydro plant, and is essentially delivering arbitraging energy on wholesale markets, providing grid services, and essentially stacking up different types of services to be able to pay back for the investment. People are expecting that if the storage technologies can reach the price points that were presented earlier in that deck, in this presentation, then the market for the storage technologies will be around terawatt hours of deployed capacity. Now, people are aware of that, and there is an increase, very dramatic increase in the funding of companies that are operating in long-duration energy storage. So according to McKinsey, the amount of funding from 2018 until 2021 going into a number of large-duration energy storage companies has increased by 90% year on year to reach about 2.6 billion, 2,600 million of investment in the sector. So definitely there is, I think, a clear sign from investors that they understand the necessity of long-duration energy storage, and they understand also that the market needs an alternative to lithium-ion that is more competitive at large scale and for long duration. So this is why we're seeing this trend. Now, I think that concludes the presentation. Thank you very much for your attention, and I think we are now, Olivier, ready to open it up to questions.
So right on time, Karim, thank you, and gives us room for questions in the audience.
Yeah, I was going to ask it, so Olivier, it's Adrian here. I mean, the energy storage sector's quite a really interesting sort of sector there. You know, you had three examples there of sort of some new technology coming, you know, CO2, compressed air. Do you have a view on which one's going to win, or do you think there's going to be a mix of these required over time? I mean, I was involved a little bit a year or two ago about some compressed air where they were using mines and some salt mines, and there's another one there as well that I had a hearing of. I can't remember, Olivier, whether it was through Green RWA or not, but it was also about sort of gravity, where there was perhaps towers with weights in, or whether there was mine shaft with weights going down as well. So I don't know if you can explain a bit more about where that, you know, what's going to come. And I know you haven't got a crystal ball, but, you know, yes, what's going to come, and you know, what would you bet on in this circumstance?
As you say, you know, I don't have a crystal ball, and I've got way too much experience in that sector to put my bet on one of those. But some investors are, and in fact, I am one such investor, having invested in a company. I won't tell you which one. But I would say my personal view, and this is very personal, and my background being in mechanical engineering, is that I trust a bit more mechanical-based technologies to last in time and to be able to be maintained and repaired and to use materials that are a lot more abundant than some of the chemistries that we're seeing in the battery space. Although some new battery companies are actually working with very very abundant materials, but focusing on large scale and focusing on availability of materials, I think my heart goes to some of those mechanical based technologies that you've mentioned before.
Yeah, I mean, I think on that, keep it simple. Because it's less prone to change, and I guess with the battery technologies, as you say, it's a scarce resource unless we start going into space and asteroids and the moon and mining on different planets, which is just a little bit too extreme, and the energy to do that's going to be excessive as well. So I'll hand over to somebody else. But thank you, Karim.
Sure.
I don't see any question on the messages. Is there any question in the audience for Karim? Yeah, Philippe.
Yeah, hi. Thank you, Karim, for the presentation. I have to be honest, I was gobsmacked. I thought I knew a little bit. I can see that I need to read again your presentation. I've got a question. You never... Maybe I fell asleep, but you never mentioned regulation. Is that a challenge in the storage industry? Because I had the feeling that in reading some paper in preparation of these events, your presentation, that there is some outdated regulatory policy there. So how do you see that?
Yeah, no, absolutely. Look, I apologize. I went very fast through that presentation, but there's actually a point on policy in one of those slides. Yes, so policy is a very important driver. Not all countries have, first of all, policies and regulations in place for energy storage. Not even talking about long duration, but even energy storage. Some countries are still ambiguous as to the classification of storage as an asset in transmission, as an asset in generation, as loads, flexible loads. So that aspect is important. But I would say on wholesale markets, which are opening up more and more to energy storage, and that's the case in the UK, where markets are very, very welcoming to energy storage, and they have facilitated the monetization of those services by energy storage, or in the US, where this is also taking off quite quickly. We have the required regulations in place. France is opening up and is evolving. We are starting to see the first transmission-connected energy storage projects. However, there is a nuance with long-duration energy storage in the sense that it will be, as a whole, a very big piece of capex, even though the marginal cost of energy capacity is lower than that of batteries. As a whole, when you look at, like a pump hydro system, even though your price per kilowatt hour might be reasonable, you still have lots of hours of discharge that are possible. So at some point, you need to be able to recover that capex through some kind of capacity mechanism, where the market incentivizes people to put capacity available, even though that capacity is not necessarily going to run very often, right? So we've seen in those slides showing the UK market and the periods of low wind that can last for 3 or 4 weeks in a row, but maybe it's a question of 10 or 15 events in the year. So how do you incentivize investors to put an asset down that's going to be used 10 or 15 times in the year and run not that much, but is actually quite critical? Because if you don't have that asset, you're going to have to run gas peakers. You won't be able to store all that energy. So that regulation, I think there's quite a lot of lobby that's being done, in particular in the US by a company called HydroStor in California, to make sure that the value of long-duration energy storage is recognized and that the right market mechanisms are put in place so it can be monetized. And it will be monetized in a different way than some of the current assets. I don't know if that answers your question, Philippe.
Yeah, no, thank you. Because it's linked to what we try to do with the association, and making sure that the finance part is going through, toward the right investment and so on and so on. And I'm from an investment perspective. If you're not clear about the regulation going around, it's a factor you have to take into account in your investment. So therefore, it could be less money through one solution and so on and so on. So thank you for that, and see that.
Maybe one more thing on that point, Philippe. So you're absolutely right. So the view on what is the revenue coming in the next years is absolutely critical for investors to move in that. But some segments, the first use case where I was showing how why you need 10 to 12 hours of storage to integrate solar power in remote community off grid. That actually, when you think about that community as a vertically integrated utility with a single operator that has the ability to decide on its optimal energy mix, then just for pure economic reasons, their incentive will be in maximizing solar power. So if you actually let a single operator decide on what is the best optimal mix to minimize the electricity cost, they will naturally go into a mix where you have long duration storage combined with renewables. And in that case, you don't need that much policy incentive. You have the economics in play for you.
Thank you, Karim. I have one question myself. If anybody has, please raise your hand or speak out. I have one question for myself on your first business case, and since construction or starting as I talk, there is on your very first business case, if you can share it again. I was interested to look for one figure that I may have missed.
Sure.
About the LCOE of the leverage cost or the average cost, I think would be the same of the energy when you mix the solar power with the LDES exactly on this one. So I think here, okay, so that's the solar plus storage on the bottom right, correct?
Over here,
the total cost of the energy blended with the long-term storage blended into it.
Yes. So it's basically saying, so if you have solar alone on a PPA, someone can offer you $60 per megawatt hour to sell you that solar power. However, when you want to store that solar power to be able to dispatch it, you need to add energy storage, and that energy storage is basically capex that is not producing electricity, right? It's not generating electricity. Actually, it's actually losing a bit of electricity in the process of storing it, but you add that capex without adding a generation capability. So that means if you count both the storage and the solar capex, and you calculate the blended LCOE of those two together, the solar and the storage, then as you increase the storage capacity, your cost of electricity is going to increase.
And these figures, I think it's critical. From my point of view, it's very critical because it kills the argument that storing intermittent energy is too expensive. In a way, I was just wondering, so there is an amortization assumption behind that graph, I believe. So this is amortized over what, 10 years to 15 years, or what's the for the capex? I mean,
this is annualized, and I believe the cost of capital that I used in this example is around 6%, I think. Oh, I have it on the slide, don't I?
So 15 years.
Okay. I don't have the cost of capital, but this is annualized. So you have replacement costs that have to be factored in and that you discount back, essentially.
Okay. Thank you. We have a few more minutes left. We have a few minutes left, I should say. If there is any more question. Okay, no, I think we're good. You've been very clear and thorough, Karim. Thank you very much. I will take if you allow me, Karim. Thank you very much for this presentation. I think it's really, this discussion was very interesting about this presentation and the discussion. I hope it gives more material for all the members and non-members. I will also say what it reminds me that I forgot to say it's the 2-year anniversary of NRWA. So we'll be publishing around it, and we hope all our members and future members find our work interesting, and maybe see you hopefully at the Bank of England session in October. Thank you, everybody.
Thank you very much.